Okay. So everybody get your spot for the midterm one. Okay, so if you have a make sure you actually do that as soon as possible. Today we're going to finish chapter 11 and move to chapter 12. Okay, there's actually not too much things for chapter 12. Okay, so we're just going through a few very key concepts that we need to actually learn for chapter 11. Okay, we talk more about the Arrhythmic equation today and give you 2 examples. Then we'll move on to the chapter 12, which is talking about the chemical equilibrium. Okay, so chemical equilibrium probably is actually things that in principle you are most familiar with because those are the things that you learn when you are in the high school. Okay, but we want to actually make it more clear to tell you the difference between chemical quotient Q and equilibrium constant K. Okay. But before we go in, any questions related to the midterm one that you are not so sure? I think in the beginning of the class, there's people ask me that are we going to have the class in the midterm 1 week? Okay, the answer is yes. Okay, so we will need to actually go into the content in the for the midterm 2. Okay, so we will still have that. Of course, I typically go much slower in the midterm 1 week because I know many of you won't show up in the lecture. And you guys are going to be very busy with your midterm 1 for a while. Okay, and what you should actually expect after midterm 1, okay, you will be able to start to review your midterm 1 on Thursday, I believe. Okay, so the first thing you can actually do after that will be actually download your midterm 1 because you will need that when you do your final exam. Okay, and I want to also emphasize this, that all the questions you encounter when you do your midterms, okay, those are valuable resources for you because at the end of the semester, we have this cumulative exams. You won't have time to go back and rewatch all the videos, right? So the most efficient way to prepare that is really focus on those questions they encounter. Okay, because the question will be still very similar. If you know how to actually do those questions, then you are more or less set. Okay, so that's actually a most efficient way to prepare your final. Okay, but get back to the midterm 1. Okay, so what is the most important thing that you should actually focus on now? What's the things that's most relevant? My videos, the in-person video is actually most relevant because every single question we discuss in the in-person lecture, they are the questions show up in the midterms. Okay, so they are. Okay, so don't spend our time trying to find some other things that you think is going to be useful. The things that's really useful and easiest to actually get to know the answer is actually watch the video. Okay, get yourself familiar with how I actually solve all the problems. Okay, so starting from there, even you don't read any textbook, even you don't read any other materials, at least you will go through 30 something questions that you know is actually part of data bank. Okay, and if you truly understand the concept we cover within these in-person lectures, all those questions was carefully picked. Because every single question is kind of represent one specific concept. Okay, so if you can really understand those 30 different type of questions, you learn 30 different type of concepts, right? Then you know that's the equations you will know like what are the equations that you will need to actually memorize. Okay, so let's count the basis of all your study. Okay, you should start from this in-person lecture. Okay, if you feel like you just want to get started now, okay, then quickly go back and rewatch the YouTube video, the in-person one. Okay, for these pre-lecture videos, it's more about the conceptual things, right? If you really want to understand the molecular concept of all the things we went through, then the pre-lecture video is actually very helpful. Okay, so if you are really good, you want to actually say, I have to get an A for this specific course so I can actually apply for the PhD or medical school in 4 years. Okay, then what else do you do? So the things I would suggest you to do is actually to get more questions, right? So last week I tell you that ACS has, I think they collect all the past exam questions. Okay, go get those questions. Not necessarily you want to actually go into their section and learn their way to solve those problems. Okay. But getting the questions is meaningful. Okay. So most of my students, what I do is actually get the questions and use my way to solve those questions. Okay. And then found that, okay, sometimes they don't know how to actually get the correct answer. They come back to me, then I show them how I think about it, how I approach those questions. Okay. That will be actually the most efficient way to get to know how to handle questions in short amount of time. Okay. So other than that, the next most important thing will be do the practice exam 1. Okay. But when you do the practice exam 1, you need to be very honest, meaning that you need to time yourself, meaning that you can only have your calculator with you, nothing else. Okay. So the goal of doing that is like you want to finish all the questions, but you still have 10 minutes or 5 minutes remains. Okay, you need to practice your speed. Okay, so many students after midterm 1, they will come to me and say, I know this question, I know how to solve it, I just running out of time. Okay, like I say in the first lecture, time is critical. Time is something you will be tested. Okay, if you cannot finish in time, you fail the test. Okay, you need to actually recognize that. Okay, so I don't have enough time. It's not an excuse that you can use to get the grade that you want for this specific course, unfortunately. Okay, so practice is very important. Okay, and practice to solve problem in a very efficient way is critically important. And I believe, okay, my way is one of the most efficient way to solve the problem. Okay, so you guys have been with me for this is 7th lecture, right? So I feel like you must have some feeling. Every time I solve a problem, it seems actually very straightforward, right? 2D pad is actually quite straightforward. Okay, so Q, D, find the keyword, I know what equation to use. Plug into the equation, I got the answer, right? That is not very simple if you are not actually practice distance for very long, right? And I practice distance for 10 years, okay? And I learned all these things 20 years ago. So I do believe that I'm in a position to actually tell you what is actually the most efficient way to do this. Okay, so sometimes students actually go to all these SEP or ACS type tutorial things, right? They'll come back to me and say, hey, that guy told me to do this, this, and that. You need to actually recognize that those tutors, they are also students. Make sense? Okay, and you're comparing someone who have been doing this for their profession. I'm professional, right? I can call myself professional in terms of teaching general chemistry too. Okay, so I would suggest that you listen to me and take my way to approach the question. Okay, if there's actually a conflict between the two, then trust me, will make your life a lot easier. Also make my life easier because you won't actually come and bug me, right? So Those count is the I think the hierarchy. I'm thinking that the things that you should actually know to better prepare for yourself. All right, and then you should actually see that now that I saying a lot of things that's not relevant to the course material itself. Okay, again, it's really I think the reason we come to get the education is because we want to learn how to think critically, right? How to think efficiently, right? So I want you to actually learn those things too, not just for the course material. Okay, because this will be actually a very important skill set you must have to be competitive. Okay. AI is going to taking care of many know-how things. Okay. But how to actually read the things and start to think critically and see what's the best way to handle a situation. Those things coming from practice. Okay, so right now we just use chemistry as our model to practice those things, right? So every time I read a question, right, I always say, okay, find the keywords. Okay, how to actually relate it to things that we learn, right? So you can quickly actually come to and narrow down your thought into a very focused topic, which is actually something our human brain can process, right? So you should actually do the same for all your courses. All right, so just actually don't restrict yourself to this course material, but apply the same concept for all the subjects you want to study in the future. All right. Okay. So if let's actually no more questions, I think everybody should have better idea about like how you should actually prepare your midterm one. Okay. So what we're going to do today first is this, right? We're going to tell you how to apply the Arrhenius equation to solve some of the questions, right? So Arrhenius equation describes how the rate constant k, the lowercase k, is related to the collision frequency, the prefactor A, and then the activation energy EA, and the temperature, right? So let's actually one of the two important equations that you need to actually memorize. Okay, so most of the time you will calculate this relationship using the natural log k equals to natural log A minus EA over RT. Okay, so the equation on the right will be probably actually the most commonly used equation you're going to apply to solve the problem, but they're actually equivalent, right? You just take natural log k on both sides and rearrange the equations. Okay, that will be actually your first equation. Every time you see a question have the keyword activation energy, there will be one of the equations you can actually consider. Okay. The second thing is actually it's actually the same equation, but right now we have to think about along the line that how the rate constant K will change when you have different temperature. Okay, so what you do is actually very simple. So we start from this really simple equation. Let's say you have two different temperatures, T1 and T2. Okay, so if you look at temperature T1, then you can write the equation natural log K1 equals to natural log A minus EA over T1. Okay, and if it's a different temperature T2, then you will say my rate constant is going to change. I will label it as K2. It's going to equal to natural log A minus EA over T2. Okay, so you can write out these two base equations. Then the things you do next is you use the equation 1. It's actually equation 1. That's equation 2. If you do a subtractions, okay, then you have natural log K1 and that's natural log K2. Then natural log A will cancels out. They'll have negative EA T1 minus negative EA T2. Okay, so these things will become natural log K1 over K2. And then you can actually pull out your EA over R, then you end up with 1 over T2 minus 1 over T1. Okay, so this is actually the equation. Okay, so this equation is especially useful, okay, to predict how the rate constant K is actually changed with your temperature. Okay, so the question will, apparently you have how many variables? You have K1, K2, T1, T2, and EA, right? You have 5 different variables. If you see a question provide 4 variables out of 5, then you know that's actually the equation you're going to use. Okay, so these are the only 2 equations in this chapter that's related to the activation energy. Okay, so one thing that student will make mistake is that you need to actually pay close attention to the orders, okay? Because here we write natural log K1 over K2, not K2 over K1, okay? So it's K1 over K2. But the temperature is actually 1 over T2 first, minus 1 over T1, okay? So you cannot mess up with the orders, otherwise you won't get the correct answer. Okay, so pay attention to this. Okay, so these are the things, the only things that we haven't really talked about much in the previous lecture. Okay, so let's go through a few questions so we know how we can actually identify the question section to use those equations. Okay, so let's look at this question. It says a first order reaction has an activation energy of 48 kilojoule per mole and a frequency factor of 5 times 10 to the 10 per second. Calculate the rate constant at 27 degrees C. Okay, what's the keyword here? Activation energy, right? So since you see this keyword activation energy, therefore you know only 2 equations you need to use, right? There's actually 1 equation you can use. The other 1 equation is actually natural log K1 over K2 equals to EA over R, parenthesis 1 over T2 minus 1 over T1, right? Since you see this keyword activation energy, therefore you know you are going to only use one of these 2 equations. Okay, you see how quickly you actually narrow down the things that you need to do. Okay, so these are things that you need to practice. Okay, so once you have this, then you can actually go back to this very simple QT pad, right? What's the specific things you need to solve? The rate constant K, right? K at 27 degrees C. Okay. So now, what's the data that you have? You know your T is 27 degrees C, right? But I need to convert into Kelvin, right? So it becomes 300 K, right? Plus 273, right? And then what else do you have? You have your EA, activation energy, equals to 48 kilojoule, right? For all the calculation, convert it to joule. So that's 1,000 joules per mole. And then you have frequency factor A, right? It is 5 times 10 to the 10th power per second. Right? That's all the information that you have, right? So with this information, which equation should you use? First one, right? How do you know? Because you only have 1 temperature, right? If you want to use the second equation, you must have 2 temperature or 2K, right? But here apparently you only have one temperature, therefore you know the equation you must use is actually the first one. Okay? So the plan will be since you actually calculate K, right? So you can actually rewrite this first to make it simple. K will equals to A times exponential negative EA over RT. Okay, so we use K equal to A times exponential negative EA over RT. A is 5 times 10 to the 10th power times exponential. EA is 48,000. R is, what's R is used? Yes, 8.314. Okay, make sure you know it's 8.314 times 300. Okay, so once you do this calculation, you will get a value of, and there will be your answer. Okay? Do you know how to get the number using your calculator? Practice it now. Yeah, because if you don't practice, people will make a mistake here. Okay. So I guess everybody have the habit, okay? So in my previous lectures last semester, okay, every time when I start to do a calculation, I start to hear people pushing the button. Okay, because I know that's actually critical. Okay, they want to make sure they can actually really do all this calculation correctly. Okay, so you should actually practice that too. Okay, so let's recap these things. Okay, first, after you read the questions, you should see that keyword activation energy. Therefore, you count down two equations, right? And then you look into your data, you only have 1K. Therefore, you know you must use the first equation. Okay. And the thing you do afterwards is plug in the number, make sure you actually push the button correctly. And that's how you solve this problem. Very simple, very straightforward. Okay, any questions? Okay, if not, let's go to the very last questions that we have here. Okay, the question says a first order reaction had a, not a rank constant, but rate constant. Rate constant of 0.52 per second at 34.1 degrees C. If the activation energy is 63.6 kilojoule, calculate the temperature in degrees C at which the rate constant is 0.979 per second. What's the keyword? No, what's the keyword? Activation energy is the keyword. Every time you see that activation energy, only two equations to go to. Okay? So activation energy, make sure you actually recognize it. Okay. Okay, so activation energy, right? So two equations. Okay, so you know these are the two that you need to actually make the choice, right? Because once you see the keyword, there's only two equations you can use. Okay. So now, once we know those are two we want to use, right? We want to actually collect a little bit more information. First is actually what's the Q that you want to solve? Temperature, right? Where your K equals to 0.979 per second, right? You want to know the temperature. Well, let's specify K, right? So what's the data that you have? You have a rate constant equals to 0.52 per second at temperature equals to 34.1 degrees C, which is 273, that's 307.1 K, right? You know you have a rate constant of this value at that temperature, right? Let's put this as K1. This is your T1. Okay? And then it says EA is 63.6 kilojoules, right? So I multiply 1,000 joules per mole. Okay. So you want to know the temperature equals to certain number where your K equals to 0.979. Okay, I will put this one as K2. Okay, so here I want to start to think. If you are standing here, can you actually write out those data yourself like that? Okay, you need to actually translate the text into those specific informations. Okay, so here, did you see that inside the question you have two rate constants, right? It actually says rate constant equals 0.52, the other rate constant 0.979. So only the second equation gives you that. Okay, so it's very clear that once you see two rate constants or two different temperatures, right? Then you know you need to use the second equations. Okay, so once you can actually recognize that, things become super easy, right? The plan will be you want to use this natural log K1 over K2 equals to EA over R 1 over T2 minus 1 over T1, right? So make sure you don't mess up with the orders, okay? So K1 will be 0.52, K2 will be 0.979. EA, 63 times 1,000, R, 8.314. T2, so this will be your T2, right? 1 over T2. That's 1 over T1 will be 307.1. Okay. Then now come to your calculation time, right? Can you actually push your button to figure out what the T2 is? Okay. So if everything is actually done properly and correctly, you should be able to get a number T2 equals to 315.1 Kelvin, which is going to minus 273, that give you 42.1 degrees C. Okay? Yes. No. Yeah. So that's actually a very common things that students have feel confused. Okay, so she is asking this term. Okay, there's actually no negative sign in the front. So the reason there's actually no negative sign in the front is because it should be R here, R here. Okay, because I only pull out this term. Okay. So the negative sign become positive. That's why your T1 over T2 goes first. So it's just a simple like calculations that lead to this conclusion that your EA over R, it doesn't have negative sign in front of it. Okay, so make sure you really memorize the equation correctly. Okay, otherwise you will put yourself in a very confusing situation. Okay, so go back to this. Let's quickly recap the things we do. Okay, again, activation energy is actually something that's so important that once you see that, you must know there's only two equations to use. Okay, and then depending on the data that provided within the questions, you should be easily tell which one is actually the one you should use. Okay, and the things you need to do is actually just memorize the equation correctly, push your button correctly, then you should be fine. Okay. So those are all the questions that we need to do for chapter 11. Okay. But before we go to chapter 12, okay, I want to actually also highlight one of the important concepts that chapter 11 covered. Okay. So this is called the this is actually pictures or figures. Okay. Let's going to put everything that you learned so far all together and going to test you all the concept of all different terminologies. Okay. The figure will look like this. The x-axis, typically you'll see this is called the reaction coordinates. Okay, so from the left side, it will be your reactant. On the right-hand side will be your product. Okay, and the y-axis will simply be the energy. Okay, so you always start from reactants. Okay, let's say your reactant have certain energies. Okay, and then you end up with product. Okay, so precision of your product can varies. Okay, so in the current things I drew, who has higher energy? Reactant. Okay, so you go from a high energy reactant to a low energy product. Okay, so I assume everybody understand energy conservation, right? So these reactions, will it be endothermic or exothermic? Exothermic. Okay, because you go from high energy to a low energy, the energy difference between the two states will release to the surrounding. Therefore, it will be a exothermic reaction. Okay, very important because in your test, it's going to give you a figure and ask you, is this endothermic or exothermic? Okay, so you must know how to actually get the correct answer. Okay, so this one will be the energy between the two. We know is exothermic. Okay, so if it is exothermic reaction, does the temperature of your solution going to increase or decrease? Increase. Okay, those are all questions going to associate with these pictures. Make sure you know the answer. Okay, so temperature is going to increase. Okay, then you're going to see something like this. And I want to make it even more complicated or general. Okay, so you see I draw this curve, right? Can you tell me where is actually the activation energy? Yes, the highest point to where? Okay, It is the highest peak, okay, to the reactant, not to the product, to the reactant. You must know, okay, the rigorous definition about how people define the activation energy. Okay? Then I'm going to ask you the number of transition states and number of intermediates. Okay, so how many transition states that you have? 4, right? How do you know it's 4? You have 4 peaks, right? So number of transition states is asking you number of peaks. Okay, so make sure you know how to count. Okay, so you need to translate transition state peaks. Okay, how many intermediates? 1, 2, 3, right? So how do you know it's actually 3? You count the number of, how do you call this? I don't know how you call this. Everybody have different names, but it's actually the dips. Okay. Okay, so it's very important that you know how to actually identify number of transition states and number of intermediates. Okay, that's one more thing I want to ask you. From this specific energy plot, how many elementary steps should be included? How many elementary steps should be included? So the answer is 4, right? So how do you know it's 4? Because you have 4 transition states. Okay, 1 transition state means you need to actually go over that to go to the next step, right? Therefore, you know, minimally, you should actually have 4 elementary steps. Okay, so the things we actually went through, is it difficult? It's not, right? But if I don't tell you all these things, when you step into the casa, you feel like ambush, right? So it's not very clear, right? But once I actually go through once with you, these questions will become very, very simple for everybody. Okay, so the thing is actually you really understand this and then prepare for it. Okay. All right, so that's pretty much all the things that I want to cover for chapter 11. Okay. Then let's move to chapter 12. Okay, so chapter 12, go back to the equilibrium. Okay. The first thing I want to actually teach you is this thing is called a chemical quotient. How many of you know what chemical quotient is? What is chemical quotient? So if you look at the equation, the Q equals to C to C's power times D to D's power over A to A's power times B to B's power. It looks exactly like your equilibrium constant, right? Okay, so what's the difference between the two? Okay, so now I want to start to think about things at the molecular level now, because once you actually see that, then things will start to make sense. Again, we want to do this most famous chemical reaction, A plus B give you C plus D, right? Okay. So every time when we start to talk about equilibrium, we need to think about from the research lab setup. Okay. How do we actually measure the equilibrium constant? Yeah, but how do we actually do that in the research lab setup then? Do you know the equilibrium constant? You don't know, right? So what do you do first? You just randomly throw in certain amount of A, B, C, and D, right? That's the only thing you can do actually. Then what? Then what? Then what do you do? Then you wait. You cook it. Okay, now you got cooked, but you cook it, right? So you start to heat up the solution. Okay? And then you heat up for a couple hours. Then you start to remeasure the amount of A, B, C, and D. Okay? And then use the amount that you got for your A, B, C, and D and the equation to calculate your equilibrium constant. Okay, everybody follow the things I say? Okay, now imagine. Do you expect the amount of A, B, C, and D the same or different before you cook the solution? It will be different, right? So it will be different. Yes, it will be different. Okay, which one is okay? After you cook it, then you think that's the K. Okay, so now think about this. Is K a constant or not? Who says no? Be brave. So how do we call K? What's the name of K? Equilibrium constant, right? If I understand the word correctly, constant is a constant. Does that make sense? Does, right? So K is a single value for a given reaction, right? So the K is a constant. Remember that K is a constant. K is a unique situation. Very unique. Okay, so it is actually a value you are going to get when the system, which is your reaction, reach equilibrium. Okay, once the system reach equilibrium, then the ratio between your A, B, C, D, they give you a constant value. Okay, everybody follow this logic so far? Okay, now think about this. Can you do the same calculation even before you cook the solution? Why not? What prevents you from doing that? Can you? See, I'm asking very simple question. So don't worry, okay? I'm not going to bite you, right? Can you? You can, right? Yes. How do you call the quantity calculate? Using the same equation to calculate the things, right? So what is that thing called? That is called the do you see this? Chemical quotient. Do you see the difference now? Q and K, they are different. K is actually a unique value, which is a constant, okay, at equilibrium. Okay, you must have this thing, you must have this thought that you can write out, you can calculate using the same equation, but have very different meaning, right? Only at equilibrium, then your Q is going to become K, right? Only under that specific condition, your Q will equal to K. Okay? Everybody see the differences now? It's very important because many students, okay, even they finish taking the CHEM2, they don't understand the difference between Q and K. Okay. So now, the other things that you must know is that the nature is magnificent. They create all these rules, make sure things happen in a specific way. Okay. One of the things that the nature and science follow is that your system always want to go to the lowest energy state. Okay. And then the state that can have the lowest energy is when your system reach equilibrium. Okay. So you can calculate your Q at any given time. Okay. And then the nature will tell your Q to change its behavior so that it will eventually look exactly the same as your K. Okay, so depending on the relative value between your Q and K, then you can actually predict how the reaction is going to move toward the product side or move toward the reactant side. Okay, so those are the key concepts. If you understand it, you'll feel like, oh, everything's actually very simple. Okay, but if you don't understand the difference between your Q and K, you just feel like, why sometimes I need to do this? Why sometimes you do that? Okay, so this thing will be even more clear when we start to talk about the ice table. Okay, how many of you have heard of ice table? Like initial change equilibrium, right? So we'll go through that too, probably actually in the next lecture, okay? But let's actually things that students always get confused, okay? All right, so with all the things we discussed, this come back to the first equation for chapter 12, which is actually the things that you know for a long time, okay? But here, let's actually one more thing I want to point out. If you look at that equation, what is actually your numerator, reactant or product? Okay, so your denominator will be your reactant. Okay, so you need to remember that. Okay, regardless if you have Q or K, your numerator always indicates the amount of product. Denominator is always your reactant. Okay, and then the ratios, okay, between these two give you the chemical quotient Q or equivalent constant K. Okay, so once we have that in mind, then you will be able to understand this statement, because one of the questions you're going to see a lot in this chapter is actually asks you predict how the reaction will actually move to the reactant side or move to the product side. Okay, the first one, if your Q is larger than your K, okay, Q larger than your K, does that means actually at the current moment you have too much reactant or too much product? Too much product, right? If your Q is really big, meaning you have too much product, okay? But you know eventually your Q needs to be equal to K, right? That means actually the reaction needs to actually move to a direction that minimize the production of product, right? Therefore, you know, you can predict that the reaction is going to move to the reactant side. Okay, so if you have that in mind, you should be able to understand why that is actually the case. Okay, if your Q is really big, right? You have too much product, move to a reactance so that I can become K. Okay, the ultimate goal of equilibrium is actually the Q need to become K at the end of the day. Okay. On the other hand, if your Q is smaller than K, meaning I don't have enough product, I need to produce more, therefore I move to the product side. Okay, so I hope this is actually straightforward for you. Okay. And this is actually something that's small, but sometimes actually show up in your quiz or midterm. Okay. We have two terms. One is called KC, one is called KP. Okay. So I want you to actually pay attention to that. The K here is uppercase. Okay. So uppercase K represents equilibrium constant. How about the lowercase k? The lowercase k represents rate constant. Okay, make sure you know. Uppercase K, equilibrium constant. Lowercase k, rate constant. Okay? So I have to say, science is actually very rigorous. Okay. So depending on the trajectory of the science development, okay, people actually keep changing the format of symbols. Okay. So this is actually kind of the finalized version. Lowercase k is always rate constant. Uppercase k is always equilibrium. Okay. So it's always good to know, okay, the notations. Okay. What's the traditional way that in the scientific field how to actually define things. So here we see this subscript, right? You see this lowercase c and lowercase p. The c means you calculate your equilibrium constant using concentration. Okay, but sometimes the chemical reaction only involve gases. Okay, so that's why you have this lowercase p means pressure. Okay, so you use pressure to calculate your equilibrium constant. Yes, so the concentration is actually all aqueous solution, right? Yeah, as long as it's actually not gas. Okay, because for the gas, that's the things you can use to describe how much molecule you have within a given volume is actually using pressure. Okay, but if you have aqueous solution or any solution, then you can use molarity. Okay, so it's really depending on what is actually things you use to calculate your K. Okay, then you can actually define the K as Kc or Kp. But both of them, they are equilibrium constant. Okay, just calculate the unit is different. One thing that you should know is that this two is actually convertible. Okay, because you can assume that the gas you have follows the ideal gas, right? PV equals to MRT. Therefore, your P and then the molarity can be actually converted from one to the other using the specific equation. Okay, so the equation that you need to actually memorize is that the Kp is going to equal to your Kc times RT to the delta n's power, where the delta n is, again, this is actually for your product. That's actually your reactant. Okay, so you're calculating what is actually the mole of gas molecule differences between your reactant and product. Okay, so it's actually number of gas molecule on your product side. You add up all those molecules, subtract the one on your reactant side. Okay, so that's actually how you convert the Kp to Kc. And one thing you want to be careful is that the R here, again, go back to the 0.082. Okay, so many students will ask me, how do I know when I should use 8.314, when I should use 0.082? Okay, the answer is actually very simple. If the equations describe gas, okay, like here, you see this P, right? Pressure, then always use 0.082. Okay, you will realize that if you actually see enough, as long as the equation involves gas, 0.082 will always be the constant you use for your R. Okay, so make sure you understand, you memorize that. Okay, will actually prevent you from making many unnecessary mistakes. Okay. All right, so let's actually the first things that we need to know. The second thing we need to know for this specific lecture is that Right now we know how to write the equilibrium constant K. Okay. So what if today I change my chemical equation? For example, I multiply a coefficient to it, or actually flip the chemical equations, and how that will actually affect my equilibrium constant K. Okay, so this is actually another type of things that chemistry department want you to know. Okay, and it's actually very simple. Whatever operation that you do will reflect to the exponent of your equilibrium constant. For example, let's say we start from this most famous chemical reaction, right? AA plus BB give you CC plus DD. Then you know we define that as your K equilibrium K1. Okay. So right now, if I flip it, okay. So think about that when you write out the equation, basically just inverse your original equations, right? Because right now product become reactant, reactant become product. Okay. So all you need to do is actually if you flip the formula going from here to here, then the new equilibrium constant will be the reciprocal of the original equilibrium constant K1. Okay. So the same thing, if today I multiply a coefficient to the overall reaction, okay, then the new equilibrium constant again will operate on your exponent. Okay. So if you multiply n here, then you also multiply n over there. Okay, so everything will change at the exponent side. Okay. And the very last thing that we need to know is that if you combine two equations, let's say K1 and K2, then your new equilibrium constant will be the product of those two equilibrium constant. Okay. And the reason is also very simple, right? Because right now, reactant in the first equation and reactant on the second equation, right now they don't belong to the same reactants, right? Then they all need to actually multiply with each other. Okay. So that's why when you add up two equations, the new K will be the product. Okay, the product, not the addition, the product of two original equilibrium constant. Okay. So any question for this so far? So if now we just do a few more questions and that's it for today. Nice and easy. Okay, so here says, consider the gas phase reaction Cl2 gas plus Br2 gas give you 2 BrCl gas, for which Kp is 32 at 500 K. If the mixture is analyzed and found to contain 0.49 bar of Cl2, 0.29 bar of Br2, and 2.1 bar of BrCl. Describe the situation. Is Q larger than K or smaller than K or equals to K? Okay. Right, so that's the questions, right? Apparently, it wants you to actually to calculate your chemical quotient Q and compare it to your K. So if you read this one, then now to actually look into the equation, right? Equation is Cl2 plus Br2 become 2 BrCl. Okay. Then it tells you your Kp is 32. Q, you don't know, but it tells you your pressure of your Cl2 equals to 0.49. Pressure of your BR2 is 0.29. Pressure of your BRCL is 2.1. Okay. So those are the data that you have. Okay. Then of course, you want to calculate your Q, right? The Q will be the pressure of your product, BRCL squared over the pressure of your CL2, pressure of your BR2. Okay, so pressure of your BRCL is 2.1. Going to do the square. CO2 will be 0.49 times BR2 is 0.29. So if you calculate this, then you're going to get a value of 30.95. Okay, so you get this, that is actually your Q, right? Be more specific, since it's actually all calculated using pressure, this is actually your QP, right? And then you compare to your KP, which is 32, right? Therefore, you know your QP is smaller than your KP. Okay? So QP is smaller than your KP means you don't have enough product, right? Therefore, you know the reaction is going to move to the product side. Okay? So let's actually how you address or solve these questions. Any question for this? Any question for this? How do I know? How do I know? I should use the 0.49, 0.29, and 2.1 to calculate the Q. You guys don't have that questions? So I give you a series of numbers, right? How do I know the number is actually for Q or for K? Okay, so that's actually another very important thing that you need to actually know. Okay. We know K is a unique special case, right? So the K represents the concentration of your reactant product at equilibrium. So if the number that provide is really for you to calculate your K, you will always see it says at equilibrium. Okay. And then with that in mind, we read this question again. Did you see this question says at equilibrium? When they're talking about all these pressures. Doesn't, right? It's how I know those numbers is not for your K. Since it's actually not for your K, it has to be for your Q. Does that make sense? Okay, so reading is actually very important. Okay, the things that you don't see sometimes is even more important. This is actually one of the case because it did not say at equilibrium. Therefore, you know whatever number it provides there is actually for your Q calculations, right? So let you know this actually start to make sense because I do this sometimes it's because of course I know how to solve the things, right? But think about it, you need to actually put you in my shoes, right? If you're actually solving this, how confident are you say this is actually Q, right? And that's actually a very rigorous reason why I know it's Q, right? Because it did not say Low's number is at equilibrium. Okay, I hope you see that now. It's very important to see that things got, never showed up in the questions. All right, so this is actually how you solve these questions. Okay, so this is actually typical questions when you start to play around with the equation that you have, okay? So it says for this specific, at a certain temperature, the Kp is 0.25 for the reaction below. H2 plus Br2 give you 2 HBr. Calculate the value of Kp for the following reaction, okay? So apparently you're actually trying to figure out the new Kp, right? And then it give you a Kp for one equation, asking for the Kp for the other equation, right? So this is actually the things we just talked about, how you actually to calculate the new equilibrium constant from the old one, okay? So how do you do this? So the way you do this, actually, you want to really, okay, so Q is, you want to have the Kp, let's say Kp2, okay? The data that you have is actually, you have H2 plus Br2, that give you 2 HBr. The Kp of this one is 0.25. And right now you have HBr becoming half H2 plus half Br2. And then what's the Kp2 is going to equals 2, right? So this is actually how you translate the questions into the equations. Okay. So every time you handle this question, you want to see how can you go from the given equation to your target equation. Okay. So the first thing that you actually see is actually, do we flip the reaction? Okay, does the reactant become product become reactant in this case? It does, right? So here the new Kp2 should be the original Kp. So every operation will happen at the exponent part, right? Or the power part, okay? So since you flip, then you must have a negative sign over there, right? So once you know it flipped, then you put the negative sign over there. Then you start to see the coefficients. What happened to the coefficients? Does it actually multiply any coefficients from the original one to give you the target one? Multiply a factor of 1/2, right? Do you see that? Going from here to here, you actually multiply 1/2, right? Therefore, you put 1/2 over there. Okay. And once you see that, you just plug in the Kp is 0.25, negative 1/2. They will give you a number of, and there will be the answer. Okay, so the things that you should really learn from here is actually, first you need to know the basic operation to calculate your new K, right? So we actually tell you the rules starting from the beginning, right? Everything you do will actually happen at the power part, right? If you flip the reaction, you put in the negative sign. If you multiply factors, you put in the factors to do the calculations. Okay, so it's actually very simple if you know those rules. Okay, so this is actually for the second questions. Okay, there's actually another one. Okay. Given the values of K shown below, determine the value of K for the reaction. Yes. Okay, so this is actually your target equation. It gives you two other equations have different equilibrium constant. Okay. Again, Q is actually trying to calculate the K of N2 plus 2O2. They give you 2NO2. Okay. Data that you have is N2 plus O2 they give you 2NO, NO2 becoming NO plus half of O2, where you have K1 equal to 2, K2 equal to 3. Okay, so this is the things that you have from these questions. Okay, so the logic to solve this is actually you want to use the one there with known equilibrium constant. You do some multiplication of each equation, then you're adding up so that you get back to the target equation. Okay, so let's call this our target. Okay, so the things that you need to know is that you have your two base equations, right? Let's call this our base. Okay. So if you look at this, in your target equations, what are your reactants? N2 and O2, right? Product is NO2. So that's the things that you need to first recognize. Okay, because you're going to have different type of base equations, right? So the first thing you do is actually you need to actually flip your base equation so that reactants actually on one side, products on the other side. Okay? So based on that, if you look at the first base equation, do you need to actually flip the first equation? You don't, right? Because your N2 and O2, they are reactant and they are actually on the reactant side. So they are fine. Don't do anything yet. Don't flip it. Okay. How about the second one? It does, right? So you need to actually first do this. Become NO plus half of O2. They give you NO2. Okay. Then I call this K3. K3 will have a value of this, right? Because it's flip reaction, right? So the new K will be 3 to the -1 power, right? And then you use your first base equation and the third base equation. When you add up the two, it won't actually give you the target equation, right? But if you look more carefully, compared to your target equation, for the third equation, maybe I should actually multiply a factor of 2. Right? So that on the product side, I can actually match my target equation. Everybody follow the things I just said? Okay. So if you think that it's actually things that you need to do, therefore you know it's become less, right? It goes from -1. Since you multiply a factor of 2, it becomes -2 now. Okay? And then once you see this, then you start to trying to add up the first and three equation. So this is actually your equation 1, equation 3, right? So if you add up equation 1 and equation 3, then you're going to get N2 plus O2 plus 2NO plus O2. That's going to give you 2NO plus 2NO2. Okay, so I just add up all the things together. Okay, then I start to actually cancel all things since 2NO show up on both sides. It cancels out, right? So you end up with N2 plus 2O2. They become 2NO2. Okay, then the new K was simply the product of your K1 and K3, right? K1 times your K3, which is 2 times 3 to the -2 power, which will equals to 0.2222. Okay, and there will be the answer. Okay, so the biggest things that we learn from here is that you need to have a clear idea about what is your target. Okay, what is your base? Your job is actually to either flip or multiply certain constant to your base equation. And after you add up, it gives you back to your target equation. Okay, and you should actually get familiar with all the calculation of your K. All right, so we'll stop here and continue the remaining part for chapter 12 on Thursday. Thank you.